Welcome to this lecture series in real analysis. In this lecture, we'll look at a very important concept, which is of uniform continuity. And primarily what we need to know and understand well to follow this lecture is the epsilon delta criterion of continuity. So let us recall what it says. Suppose we are given a function on a subset S of reals. Then by definition, f is continuous if it is continuous at every point in the domain. And what does that mean? What does it mean to say that f is continuous at a point A? It says that for all epsilon greater than 0, there exists delta greater than 0 such that if we choose x with this property and in the domain, this is A in my notation, we have the following, right? But the crucial thing is that this when you are given a point A and you've chosen an epsilon, this delta may depend on the point A. Meaning, if you have a different point, let's say B in S, and f is continuous there, and you have chosen some epsilon to which you need to respond by some delta, the same delta may not work for the point B. You may need to choose a smaller delta to satisfy this condition, So different points may have different demands. A may not be very demanding, in which big deltas may also work for a given epsilon, but a different point may be very demanding. So what I want to stress is that the choice of delta is contingent upon at which point we are talking continuity of the function of. Okay. So with that, let us proceed. Here are some problems for practice. And now let us get started. So let us define the notion of uniform continuity. We are given a function from a subset S of reals to reals. And we say that f is uniformly continuous if, roughly, the same delta works everywhere. Roughly, that is the idea. But what is the formal definition? It says that for all epsilon greater than 0, there exists delta greater than 0 such that whenever we pick 2 points in the domain which are distance less than delta apart, we have the corresponding points in the images are less than epsilon apart. So here, once you've chosen an epsilon, no matter which x you choose, as long as y is chosen within distance less than delta from x, the image points will be epsilon close. So the same delta is working uniformly everywhere. Different points do not demand different deltas. That is uniform continuity. Even though the definition, so one thing should be clear is that if f is uniformly continuous, then f is continuous. That should be clear. So uniform continuity implies continuity, but still it is unclear if the reverse is false. It should be false because the definition looks, at least apparently, more restricted. Also, there is no point-wise notion of uniform continuity. Uniform continuity is by definition a global notion. We cannot talk about uniform continuity of a function at a point. We can talk about locally, uniformly continuous and whatnot, but let's not get there. Okay, so it's a definition as of now. The importance of it is as of now not apparent, but let me assure you that it is going to be a very important notion for us. Okay, so let us see an example where you have a function which is continuous but not uniformly continuous, which will make it very, very clear to us that this notion is a strictly stronger notion of continuity than just plain continuity. Okay, so here is the example. We have a function defined on all positive reals to the real numbers, defined in this fashion. And this is the graph of the function. Clearly, this is a continuous function. we will show that this is not uniformly continuous. Let me write a few things and then explain the idea behind what is going on. It's a very simple thing. So assume f is uniformly continuous. Okay, and choose epsilon as 1. Now by uniform continuity, there is some positive delta such that whenever we choose 2 points in the domain of f, which are distance less than delta apart, the corresponding points in the image are less than epsilon apart, but epsilon is 1. And let me just show you in the figure that this cannot be true. So why is that? So choose a positive x and choose y as x plus delta by 2, let's say. So this is x and we choose y as x plus delta by 2. And we record the difference in the image points. That difference is this vertical distance. Okay? This vertical distance is what appears here. Alright, and it should be visually clear that as you slide the point x to the left, keeping y as equal to x plus delta by 2, so as you slide this line segment towards the left and keep coming closer to the origin, this vertical distance keeps on increasing. You can animate this in your mind. Right? So if I had chosen x very close to the origin, move the distance delta by 2, I will detect a lot greater distance. And at some point, this distance will exceed 1, contradicting this. So even for epsilon equals 1, the uniform continuity, the demand for uniform continuity does not hold. And therefore, f cannot be uniformly continuous. But let us give a formal justification. So what I said was the following. So by what has been written, we have if, or rather for all x, we have this thing must be less than 1. Right? We are just choosing y as x plus delta by 2. So this condition is satisfied. And since x is positive, both x and y are positive. So this immediately implies that this must be true for all positive x. But here we will get a contradiction because what is the left-hand side? It's this number. We can remove the absolute values because this guy is a positive real. And we get this is true for all positive x. But that is absurd because this thing takes arbitrarily small values as x becomes arbitrarily small. Right? So this cannot remain greater than delta by 2. And therefore, we have a contradiction. So f cannot be uniformly continuous. Alright, so we have a continuous function which is not uniformly continuous. And this should convince you that uniform continuity is a strong demand. Okay. But all is not lost. In a sufficiently general or a sufficiently useful setting, continuity does imply uniform continuity, and that is what we turn to next. So here is the lemma. Suppose we have a continuous function, we have a continuous map, and the domain is a compact set. Recall, compact sets are the same as the closed and bounded sets. We proved that. This is called the Heine-Borel theorem. So if the domain of a continuous function is compact, then the function is automatically uniformly continuous. Compactness is a great property to be dealing with. This is one of the reasons why compactness is such a nice thing to be dealing with. Okay, so let's try to prove this. So fix an epsilon greater than 0. And let's write down what are we trying to prove. We are trying to show that there exists some positive delta such that whenever we choose 2 points in the domain which are distance less than delta apart, the image points will be distance less than epsilon apart. So that's what we want to prove. Okay. So here is what we will do. So for each A in A, we know that there is some delta A. So this delta depends on the point A chosen, such that if we choose a point X in this delta neighborhood and in the domain of the function, we get, and here we need to pay attention, this is epsilon by 2 is what I'm going to write. Okay. So I haven't cheated or anything. I have just used the epsilon by 2 delta criterion. Epsilon by 2 is a positive number. So there is some positive delta which responds to it for the point A because the function is continuous at the point A. The function is continuous everywhere. So for each A, we can find a delta A such that whenever this happens, this happens. And let me diagrammatically arrange that. Now in this diagram again, I have drawn things like, the set A is not at all looking like a subset of reals, but it is a subset of reals. I have drawn it in this fashion just for visual convenience. Okay. So this circle that I've drawn denotes VA. Even though it looks like a circle, it is after all the interval. So this interval is VA. In the figure, it is looking like a circle. Okay. And let us also define UA as that. So its width is half of the width of VA. And in the figure, what we will draw is a ball of half radius. Hopefully this is accurate. It's not accurate, but yeah, okay. So this pink thing is UA. All right. So just to recap, whenever we choose a point in this blue ball, the F value at A and the F value at that point differ by at most epsilon by 2. That is how this blue ball has been chosen. And the red ball is sort of half of the blue ball. Again, when I say balls, I just mean intervals. Just for the explanation's sake, I am drawing it in this fashion. Okay. So now define this script C as the collection of all the half balls, the pink balls. Okay. And clearly this is an open cover of capital A because each UA is open and every point in capital A is in some UA. In fact, if you pick little a in capital A, little a is lying in UA. So this is an open cover of the set capital A. And therefore, by compactness of A, we get there exist finitely many points in the set A such that the corresponding pink balls cover the set A. Okay. So far so good. It's unclear why we are doing all of this, but soon you will see what is the reason for all of this. Okay. Now we will create our delta, the promised delta. So define delta as the minimum of all these things. So the pink balls together cover the entire A. We are choosing delta as the smallest radius of all these pink balls. Delta A1 by 2 is the radius of the pink ball UAI or UA1. Okay. So delta is the smallest radius of all these pink balls. All right. And this is our claimed delta. We'll show that this delta works, meaning whenever we pick 2 points which are less than distance delta apart, the image points are less than epsilon apart. So that is how the proof will finish. Okay. So to do that, let x and y be in A such that their distance is less than delta, we will show that the image points are epsilon close, which will finish the proof. This is what we want to show. The same colored things. Okay, so why is that? So x is going to lie in some of these pink balls. So say x is in UAI, right? These pink balls, UA1 up to UAK, they cover the entire set A. So x is going to lie in one of them, and that is what we have drawn here. So this is AI, center of this pink ball, and x is inside it. All right. But now here is the crucial point. We claim that y is in this blue ball. Y is in the blue ball. I shouldn't have written that in pink. Okay, so why is that? So the distance between x and AI is less than delta, and hence less than delta AI by 2, because delta is the smallest amongst all those. So that is what it means to say that x lies in this ball. Yeah, so okay, just to rewind. We already know that the distance between x and AI is less than delta AI by 2 because x is lying in this pink ball. X had to lie in one pink ball, at least some pink ball, and let's say this is that pink ball. So the distance between x and the center is less than the radius, and the radius is delta AI by 2. Fine. So this distance is less than delta AI by 2. But what is the distance between x and y? The distance between x and y is less than delta, and hence also less than delta AI by 2. So from AI you go to x, covering distance less than delta AI by 2. And then you go to y, again further covering distance less than delta AI by 2. So in total you will not be covering more than twice of delta AI by 2. And hence the distance between y and AI is less than delta AI, which is exactly what it means to say that y is in VAI, because the radius of VAI is delta AI. So I hope you followed that reasoning. It is just an application of triangle inequality with this and with the fact that x and AI are close by delta AI by 2. So we have justified that claim. You can write down the proof of it in your notes for yourself. And that's it. So since x is in UAI, it is in particular also in VAI. Okay. So we have that, and hence by the choice of AI, we have, or rather the choice of VAI, we have this thing is less than epsilon by 2. That's how we chose the VAs, so that this becomes true. And again, the same thing for y, because y lies in VAI, we have, that is the case. But let me write this in a flipped way. Let me write FAI first and FY later. And now we just apply triangle inequality here. So we just add these inequalities to get this is less than epsilon by 2 plus epsilon by 2, which is epsilon. And this thing is greater than the absolute value of the sum of these things. That is the triangle inequality. So this thing is at least that. So we get that this is less than epsilon, and we are done. That finishes the proof. It's a very nice proof, and it is a very good idea to go over this proof until one digests it. This has an interesting idea. The natural choice would be to cover the set A using VAs itself, but you will soon see that doesn't work, and which is why this adjustment was made. You cover them by half balls, and then find finitely many of those which also cover it, and then proceed. It hides a very nice idea in it, and this will be frequently used throughout your mathematical career. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.